All right, welcome to lecture 6. So today we're going to start chapter 3, computer arithmetic, and we're going to start with some basic things such as significant digits and rounding. So a computer contains only a finite amount of storage space, so it can't compute with real numbers without approximating. You have to truncate eventually because you have a finite amount of space and it's limited by the computer's ability to deal with the numbers. So in this chapter, we're going to see how this is handled in a computer. The first thing to keep in mind, and we'll see that a little later, is that computers deal very differently with integers and real numbers, okay, and how they are stored in memory. We're going to see this in the next class. Because there are errors that can be introduced when you're approximating and when you're computing with approximations, it's important to understand the basic principles. So in particular, the precision of a computing device is defined in terms of significant digits, which brings us to this first basic definition of significant digits. So roughly said, this is something that measures the accuracy of a measurement approximation, okay? And so to illustrate this, I'm going to give you two little examples. So suppose that you're on a package, you're reading that what you're buying has a weight of 28 grams. Whether it's written as 28 grams or 0.028 kilograms, the amount of information in these two ways of writing the numbers is exactly the same. On the other hand, if you're buying something that says that it contains 0 grams of fat, or it says that it contains 0.0 grams of fat, intuitively you feel that 0.0 gives you more information, right? That you know that if it says 0 grams of fat, there's a chance that it's like actually 0.99999 grams of fat. So by telling you that it has 0.0 grams of fat, you feel, I mean, in a sense that you have more information, which is what significant digits is about. So on in the first example, 0 grams, I mean, in this example, when we write 0 grams, there's one significant digit. But if you write 0.0, there's actually two significant digits. So there's more information conveyed in the second version. Okay, now the definition I'm going to give you, which is from the book, is ambiguous. So there are cases where it is not, the definition is for certain ways of writing numbers, it's not going to be well defined. And that's why one of the reasons we use exponential notation, which we will see after. So bear with me for now. Okay, so I'm going to define the notion of significant digit just the way it is defined in the book. But keep in mind that in certain cases, it is ambiguous. It won't be a problem for us, okay? Okay, so here's the definition of significant digits. So first of all, a non-zero digit is always considered significant. Second, the 0 digit is considered significant if it is in between two significant digits, okay? Third, the digit 0 is not significant if it's before all non-zero digits. And if there's a decimal point, then all the trailing zeros are considered significant. Think of 0.0 grams, okay? That's a good example to keep in mind. Okay, now there's an ambiguous case, which is the remaining case, if you wish, if you think about it. So if there is no point, if there's no decimal point, and there are trailing zeros, are these significant or not? Well, we won't bother with that, okay? If you're using exponential notation, this is impossible. It's not going to appear, so we won't care about that, okay? I'll still throw in a few examples of this ambiguity so that you know where it lies. Okay, so why is this? If you write down 12,345,900, those two last zeros, they might not be significant in the sense that they don't convey any specific information, in the sense that in decimal we tend to round to the nearest tens or hundreds, right? So maybe the measurement was just roughly just about this number, when in fact the actual value could have been 1, 2, 3, 4, 5, 9, 4, 3, for example. Okay, so here are some examples. So 3.14 has how many significant digits? Well, that's 3. That's pretty easy, right? They're all non-zero. They are significant. 1, 2, 3, 4, same thing. This has 4 significant digits. They're all non-zero. 56.607, so we have 4 non-zero digits, and there's a 0 digit, but it's in between non-zero digits, so it's significant, so that's 5. Exactly the same idea here. 880.077, everything is significant, that's 6. This one is important, so the zeros there in front are not significant. They don't mean anything. Think about it this way. You could rewrite this number in a different way without those zeros, right? And you'd get the same amount of information. So 0.000345 has 3 significant digits. That's where the information is. 7.7700. So here again, think of the 0.0 gram in the box, right, on the box. So here you have 5 significant digits. So those trailing zeros are significant because there's a decimal point. So they indicate a better precision. How about this one? Well, again, the leading zeros are not significant. The 7s are significant, and the trailing zeros are also significant. They're after the decimal point. So that should be 5, right? Yes. Finally, this one, this is the ambiguous case. We won't bother with that. We don't know. Okay. All right. Now, once we know what significant digits are, okay, then it's easy to define what's the most significant digit and the least significant digit. That's easy, right? So the leftmost significant digit is what we call the most significant digit, and the one that is the last one on the right of the significant digits is the least significant digit. Okay, so let's take a look. So 3.14, we agreed that these are all significant. So 3 is the most significant digit and 4 is the least one. 1, 2, 3, 4. Again, this is easy. 1 is the most significant digit, 4 is the least. 56.607, everything is significant here. So 5 is the most significant and 7 is the least. Again, here, everything is significant. So 8 is the most significant digit and 7 is the least. Here, the leading zeros are not significant. So the most significant digit here is 3 and the least is 5. 7.7700, again, those trailing zeros are significant after the point. So 7 is the most significant and 0 is the least. Again, those leading zeros are not significant. So 7 is the most significant digit and 0 is the least. And this is ambiguous. Clearly 5 is the most significant digit. It's certainly significant as the leftmost digit, but we don't know what the least significant digit is. And again, this doesn't matter. Okay, this is the ambiguous case. Okay, here's a little aside. There's something very interesting about significant digits in very large tables of numbers. At some point, somebody noticed that, now you would think that if you have very large tables of numbers, that if you look at the most significant digit of all these numbers, that it would be uniform, right? So that any number is as likely as any other number to appear, right? If you have very, very large tables of some measurements or something. But actually, It's not the case. This is something called Benford's law, which is way beyond what we're doing, but it's interesting to mention. It's very counterintuitive that, in fact, 1 is way more likely than any other digit to appear as the most significant digit. Then 2 is the most likely after 1, and then 3. And as you go down right up to 9, these are less and less likely. This is used as a method to check for fraud. There are some very famous examples that some tables had actually been manufactured and rather than obtained in a natural way. That's another story. Okay. Okay, so we are going to consider now something called round to even rounding. So we want to discuss rounding, which is something which you've done before, which most of us have done at some point or another, which means basically approximating a given number by removing some decimals, right? So I'm going to talk about something called statistician's rounding, or round to even, which is a bit different from the method that you are probably familiar with, but it's almost the same. It's very similar. Why are we considering this? The idea is that if you have a table with a lot of numbers and you round with the usual way of rounding, you are going to skew the average up. So in order to try to keep the average of the values in your table roughly the same as it was, you do it this way. Okay, so you'll see that depending on the parity of the test digit, we're going to do different things. Okay, so again, what do we mean by rounding a number? We mean that we're going to drop some decimal, some digits. Now, this is important, something called the test digit. This is the leftmost digit which is dropped, okay? So it's the first digit in the number that you actually will remove, okay? Okay, so when do we round down? So you look at the test digit. If it's less than 5, then nothing has changed, right? You just drop the digits and that's it. That's like the normal way of rounding, right? Rounding up, okay? Suppose that your test digit is bigger than 5 or is equal to 5, and after that there's a non-zero digit. Then you round up, which means that you add 1 to the preceding digit, right? So you're rounding up. So this is exactly the same as we would do in normal rounding. Now, the only difference is the following, which is called the odd add rule. So suppose that the test digit is equal to 5. Everything after is 0, okay? Then you look at the preceding digit, okay? So just a few minutes ago, I said the parity of the test digit. I'm sorry, that was wrong. So it's the parity of the preceding digit, the last one that you don't drop, okay? So if it is even, you don't change it. And if it is odd, you add 1. So half the time you keep the thing as it was, and half the time you go up, okay? So that's why the average is going to stay balanced. Okay. So here are some examples. Suppose that we are asked to round the given numbers to 2 decimal places. So that means that I want to keep 2 decimal places, okay? So how do I round? I have to find the test digit and apply the rule, okay? So if it's 2 decimal places, then the test digit, this is going a bit fast, okay? So the test digit is, in this case, 4. Right? This is less than 5, so I just chop off 482 and I get 1.73. Okay. 3.1416, the test digit is 1. So I just drop everything and it's 3.14. Nice and easy. 0.0037, the test digit is 3. It is less than 5, so 0.00. Okay. 0.5677, test digit is 7, which is bigger than 5, so I go up 0.57. Okay. That special rule, that new rule that you might not have known before, we haven't applied it yet, so it's not in these examples. 258.678, the test digit is 8. That's bigger than 5, so I go up. So I should get 258.68, like that. Oh, one last one. So 0.00911, the test digit is 9, which is bigger than 5. So I should add 1 to what I'm not dropping, so that's 0.01. Okay, so all of these examples are just normal rounding. It's the same thing as the method that you're probably familiar with. So now in these examples, we have to round the given numbers to 1 decimal place. Okay, so here the test digit is the second decimal, which is 5, right? Then I look after, there's a non-zero decimal after my test digit, so I go up. So that's 1.2. Okay. 22.250070. Test digit is 5. I look further down the road, I see a 7 there, so I go up 22.3. 3.35. Okay, here we go. So now my test digit is 5 and everything after is 0. So now this is my special rule. So I round to even, right? So 3.4, 3.3, 3 is odd. I go up to 3.4. Okay. If I have 36.6500, my test digit is 5. There is nothing after that, which is non-zero. So it's that special rule again. Now my last digit that I'm not going to drop is 6. It's even, so it stays the same. So this will be 36.6. Okay. 7.85, test digit is 5. Nothing after. So I look at 8, it's even, stays the same, 7.8. 9.9500, test digit is 5. Nothing but zeros after. So I round to even. So I look at the digit, it's 9, have to go up. I add 1 to 9.9, I'm going to get 10.0. Okay, so all of these, the last 4 examples illustrate this special rule, okay, that might be new. Okay, now here is like maybe the trickiest examples you're likely to see. So here we're asked to round the numbers to a certain number of significant digits. So you have to be able to figure out what the significant digits are and round properly, okay? So 0.77777. So all the 7s there are significant, not the 0, right? I want to keep 3 significant digits. So here I've outlined, you see in red, this is the test digit. It's bigger than 5, so we go up, so 0.778. 5.4321, everything here is significant. So the 3 first significant digits are 5, 4, and 3. The next one is 2, so that's our test digit. It is less than 5, so nothing happens. I just keep 5.43. 66.6503, everything here is significant. So the 3 significant digits, the first 3 are 66.6. Test digit will be 5. And so I look after that, there's a 3, so I go up, so 66.7, yes. 888.5, everything is significant. So the test digit is that 5 there. There's nothing after it, so it's my special rule. But the digit before is 8, it's even, so nothing happens. Finally, 333.5, everything is significant. So the first 3 significant digits are 333. So my test digit is 5. There's nothing after. Digit just before is odd. So we go up +1, 334. Okay. So if you manage to go through this last example easily, that means you've understood everything here. Okay. Now, truncating, where I'm going to finish with this. Sometimes rather than rounding, you just truncate. You just drop the digits without doing anything else. That's the simplest way that you can fit your numbers, right? So here, let's say we're asked to truncate to 3 significant digits, okay? So you just pick out 3 significant digits and drop everything else. So 88.77, everything is significant. So you just drop the last 7, that's it. Minus 7.8989, yeah, the minus, we haven't seen negatives yet, but it makes no difference, right? It's not relevant to these definitions. So if I want to keep 3 significant digits, 7.89, you just drop the rest. So minus 7.89. 999.111, so you just drop everything except the 999. And finally, minus 0.012345. Notice the first zeros are not significant. This is important. So 1, 2, 3 are the first 3 significant digits. You drop everything else. So this is minus 0.0123. Okay. So next time, I will start exponential form. And then we will go to the internal representation of integers and real numbers in the computer. So I'll see you next time. Cheers.